Let's examine Dijkstra's algorithm through our same example. At the initiation step of the algorithm, node U will only update the cost to its direct neighbors, X, V, and W with costs 1, 2, and 5. Note that at this step, the route to W will have the cost 5. The algorithm will learn a better route to it later. The cost of reaching all other nodes, which are Y and Z, are also set to infinity at this step. They will be updated as we progress. In the first iteration, the algorithm starts examining the nodes starting from the least cost node. It will start with node X. The cost of reaching Z will be cost of reaching X plus the cost of link from X to Z, which is infinity. In the same step though, the algorithm will examine reaching Y and W through X and update their associated costs from infinity to Y and 5 to W to new values of 2 to Y and 4 to W, both noted through X. The cost of reaching Z still remains infinity at this step of the algorithm. Now starts the second iteration. It now has two nodes, Y and V, with the least cost of 2. The algorithm can choose either of these nodes to move forward. Let's proceed with Y. The cost of reaching Z through Y is 2 plus 2, which is 4. So at this step, we have a path to Z, which is through node Y. At this step of the algorithm, the path to node W will also be updated to be through node Y and with value 3. Then we start the third iteration with node V, which has the least cost among the unexamined nodes by far. There will be no new updates within this step to the route to Z or any other nodes in the network. The fourth iteration is examining node W. There will be no updates by end of this iteration as well, neither to Z, as it already has a path with a lower cost, and nor to other nodes. The fifth iteration will be examining node Z. The least cost path to Z by far is the minimum among those calculated in previous steps. There is no node that could be reached with a lower cost from Z either. So, no new updates. Having examined all nodes of the network, X, Y, V, W, and Z, the node U will have the least cost path to node Z, as well as all other nodes in the network by the end of iteration 5. Note that it will have the full path to the nodes, as well as the cost of the path. The resulting forwarding table at node U will have the destinations in the network with the next hop, or the first link to take to reach that destination. This is exactly the same forwarding table resulted using distance vector with Bellman-Ford algorithm as we saw before for the same network. For example, to reach node X, the direct link U and X will be taken, and to reach node Z, also the link U and X will be taken, with next hop being X. However, the distance vector algorithm does not have information about the rest of the network, but the link state algorithm, Dijkstra, has that information, knowing exactly which links are selected on the path to the destination. Therefore, it will not experience problems as count to infinity. We learned about both of distance vector and link state algorithms. Now, which one should we choose? Let's compare them on a number of parameters. In the link state algorithm, the nodes need to know about the entire network. Therefore, the message exchanges happen for all of the nodes for each of their connected edges, which, if there are n nodes and e links in the network, will be in the order of ne. In distance vector algorithms, updates only propagate to neighbors. This limits the number of messages exchanged substantially. The link state needs to compute path from each node to every other node in the network. So it converges in n to the power of 2 in the loop we saw. Distance vector may encounter problems like routing loops and count to infinity, affecting the convergence boundaries for these cases substantially. In linked state algorithms, error on the incorrect advertised link will affect the incorrect advertised link only. Due to limited information from neighbors in the distance vector algorithms, an error might propagate through the entire network and affect other nodes. Linked state algorithm needs a lot of storage as it stores all links on paths within the network. Distance vector algorithms store limited information and therefore will not need a lot of storage.